Okay, so when I was asked to give this talk, I actually panicked because among the co-authors here, I am the one who know the least about this work, but I'll try my best to tell you what we did based on my understanding. So before I begin, let me tell you who these people are. Vibhav is my colleague. He's a super expert on approximate inference. Deepak is his student. Chen is my student. This talk is about applying Markov logic networks to event extraction. And as an NLP person, I find it extremely frustrating that when I gave an NLP data set with 1 million features to these off-the-shelf packages for MLNs, no matter how long I waited, I'd never be able to get back the results. And so Vibhav and his students have all sorts of tricks to get things to work, but they admitted that existing off-the-shelf MLN packages are not designed to handle 1 million features. And in this work, they actually apply one of the very simple tricks to make MLNs work for event extraction. Let me first remind you that event extraction is a task of extracting and labeling all instances in a text document that correspond to predefined event types. And the bio-NLP Genia event extraction task, which is a task that we are focusing on in this work, concerns the extraction of instances of biomolecular event types. And so let's take a look at this example. Blah, blah, blah demonstrated that HOIL1L interaction protein is recruited to CD40 in a TRAF2 dependent manner. Here you can see that each event is represented by the event type, a word that identifies the event known as the trigger, as well as the participants known as its arguments. And here, from this text segment, we can extract 2 events. A binding event whose trigger is recruited. It has 2 arguments, HOIL, interaction protein, and CD40. In addition, we have to assign a row to each of the arguments. And in this case, both arguments have the row theme. Here, we have another event, E2, which is a regulation event and have the trigger dependent. And here it has 2 arguments. The cause argument is TRAF2, and the theme argument is actually another event, E11. And so you can see that events can be nested, and that makes this task difficult. Okay? So let me tell you what the standard pipeline approach to this task is. It's a pipeline approach that involves 3 steps. In the first step, we have to detect if a token in a document is a trigger, and if so, we want to assign an event type. Sometimes we call it a trigger type to this token. After that, we want to determine for each of these detected triggers all of its arguments and assign a row to each detected argument. And finally, we have to combine the extracted triggers and arguments to produce events. And here's a note. Steps 1 and 2 are pretty difficult for event extraction, while step 3 is fairly trivial. And so we'll focus on the first 2 steps in this talk. Okay? So let's take a look at the pros and cons of this pipeline approach. The pros are that this approach is simple and straightforward, and it typically uses an efficient learning algorithm like an SVM in each step, and that enables the use of high-dimensional features. So what do I mean by high-dimensional features? Features such as the n-grams of the context words, n-grams of the words, part of speech, dependency relations extracted from a dependency path, and these are features that are important for the event extraction tasks. And what are the cons of this approach? Well, errors may propagate from one stage to another. And since each trigger or argument is detected independently, this approach fails to capture the relationships between neighboring triggers, neighboring arguments, etc. Despite its weaknesses, the pipeline approach actually achieves state-of-the-art results in the bio-NLP Genia event extraction tasks. And so the question is, can we improve further? And if so, how? Well, one way to improve is to try to overcome the weaknesses of this pipeline approach. And so one possibility is to make use of joint inference using Markov logic networks. The pros of MLNs is that they can avoid error propagation by jointly detecting triggers and arguments. And also these MLNs can model dependencies between triggers and arguments easily. Okay? But the performance of existing MLN approaches to event extraction lags behind that of state-of-the-art pipeline approaches. Why? Because they include a highly simplified model ignoring powerful high-dimensional features. But why do they include a highly simplified model? Because modeling high-dimensional features using MLNs is difficult. But why is modeling high-dimensional features using MLNs difficult? Because the complexity of inference is high. And so let's take a look at this formula in an MLN, which involve a word W2 as well as the words to its left and right, W1 and W3. And as you can imagine, this formula actually models a simple trigram feature. And it requires the number of groundings of this formula is actually cubic in the number of words for each position. By groundings, I mean an assignment of values to variables. And so, since you have 3 different words, the number of groundings in this case would be cubic in the number of words. And so our goal here is to combine the strengths of the pipeline approach and MLNs for event extraction. Again, the strength of the pipeline approach is that it can handle high-dimensional features. And the strength of MLNs is that they can handle or capture relational dependencies. And more specifically, we want to propose a model for event extraction based on MLNs that can handle high-dimensional features. So here's the plan for the rest of the talk. We'll first give you an overview of the linear event extraction task, as well as some preliminaries of Markov logic networks. And then we'll describe our baseline system for event extraction, and then our MLN approach for event extraction. And finally, I'll show you some evaluation results. So let's start with our overview of linear event extraction. So the linear event extraction task was being organized in 3 years, 2009, 2011, 2013. In 2009, it involved only event extraction from abstracts. In 2011, it involved event extraction from abstracts as well as some full text articles, whereas in 2013, it only involves event extraction from full text articles. And so you can see that the complexity of the task has grown over the years. But in all these 3 years, the task is concerned with extracting instances of 9 fine-grained event subtypes that can be categorized into 3 main types, namely simple events, binding events, and regulation events. Simple events can take a protein as its theme argument. A binding event can take 1 or more proteins as its theme argument, and so they are more difficult to extract than simple events. And finally, regulation events can take 1 protein or event as its theme argument, and optionally 1 protein or event as its cause argument. And so you can see that regulation events are the most difficult to extract events because of its recursive structure, as well as the possibility of having an optional cause argument. Okay? So let me give you a very, very brief overview of Markov logic networks. So a Markov logic network, or an MLN, is a set of weighted first-order logic formulas, Fi and Wi, where Wi is the weight associated with formula Fi. So a formula specifies a hard or soft constraint on predicates, and a weight specifies how important it is to satisfy the constraints. So for instance, if you have a hard formula like x is the father of y implies y is the child of x, we should give it an infinite weight if we want it to be a hard formula. Whereas if we have a soft formula like if x is the mother of y, then x is below 45. We know that's not always true, and it's most likely to be a soft formula, and so we would give it a finite weight. Okay? Now, we talked about this before. Grounding of a formula, it's an assignment of values to the variables in the formula. So in this case, we have this formula mother xy implies x is below 45. If each of x and y has 10 possible values, then the formula would have 100 groundings because we have 10 values for x and 10 values for y. Okay? Some more terminology. A world omega is an assignment of values to all the ground predicates. So for instance, a will may assign the value true to the ground predicates father, Bob, John. It may assign the true value false to father of Bob, Ted, etc. And the probability of a will omega is given by this formula, where n of Fiw is the number of groundings of formula Fi that evaluates to true under this world omega. And z is just a normalization constant. And as you can imagine, or intuitively, omega is more probable if more formulas in the MLN are satisfied more often. So that's the intuition. And as you can imagine, the key inference task over MLNs is finding the most probable will or the highest probability will. It's also known as the map task or the MAP task. Okay? So now let's take a look at our baseline system for event extraction, which adopts the standard pipeline approach involving trigger classification followed by argument classification. And so let's take a look at trigger classification first. To train the trigger classifier, we do the following. We create one training instance for each candidate trigger in each training document, where a candidate trigger can be a verb, a noun, or an adjective in the associated text. The class label of the instance is the event type if the candidate trigger is indeed a trigger, and the class label is none if it's not a trigger. And as our learning algorithm, we use SVM multi-class. Here are the features that we use to represent each instance for the trigger classifier. We use both token-based features and dependency-based features. And almost all of these features are used in previous work for this task. We're not going to go over all these features, but what I want to point out is that we do have these high-dimensional features like word n-grams of the trigger, as well as its context words, and n-grams formed from the stem words or the part of speech tags of the words in the dependency path. And so in total, we have over 3 million features. And now let's take a look at this argument classification component. Again, to train the argument classifier, we create one training instance by pairing a candidate trigger T with one of its candidate arguments, where a candidate argument is either a protein or a candidate argument that appears in the same sentence as the candidate trigger. In this case, the class label is the row of the argument if the candidate argument is a true argument of the trigger, or otherwise the class label is none. And as before, we use SVM multi-class as the underlying learning algorithm. Again, these are the features used for training the argument classifier. Again, we have many high-dimensional features, just like the case for the trigger classifier. So now let's take a look at our MLN approach, where the goal again is to design a model for event extraction that combines the strengths of SVMs and MLNs. Again, we want to be able to employ high-dimensional features and at the same time model the dependencies between different data instances. And here's an overview of our MLN approach. The first step is to learn the SVM trigger and argument classifiers using these high-dimensional features, just like what we did in the baseline. And the second step is to design an MLN whose formulas encode the soft and hard constraints on the predicates. And finally, we'll encode the SVM output as prior knowledge in the MLNs. We have already talked about the first step is just the baseline, and so let's take a closer look at the second step. So our MLN, which we call the bio-MLN, has 3 kinds of predicates. Query predicates are those whose assignments are not known and therefore need to be predicted during inference. And we have 2 kinds of query predicates. Trigger type encodes whether the token located in sentence SID at position TID has trigger type T-type. Whereas argument row is a predicate that encodes whether the token in sentence SID at position AID plays the argument row A row with respect to the token at position TID. Okay? And this exclamation mark here means that exactly one of the trigger types makes the predicate true for each combination of sentence ID and position ID, and that's reasonable because each trigger cannot possibly have more than one trigger type. There are these hidden predicates that model latent random processes. And in this case, we have a simple predicate which encodes whether the token in sentence SID at position TID corresponds to simple or a binding event, whereas the regulation predicate specifies whether the token in sentence SID at position TID corresponds to regulation event trigger. And finally, we have these event predicates that are always assumed to be known during inference. And in particular, we have 2 kinds of evidence predicates in our MLN. The word predicate encodes whether the word in sentence SID at position TID is equal to this word. And this predicate dependency type encodes whether D type is the dependency type in the dependency parse tree that connects the token at position TID to the token at position AID in sentence SID. Okay? So here are the 9 formulas based on these predicates that we talked about earlier in our MLN. The first 2 asserts that each candidate trigger or argument has a type or row. And here we have our hidden predicates that are the definitions of the simple predicate and the regulation predicate. So again, we have simple events and regulation events. And so these two formulas define what they mean. These are the formulas that capture the dependencies between triggers and arguments, because you can see that they connect the trigger type and the argument row predicate. And so are these formulas, because if you remember, the simple predicate and the regulation predicate are expressed in terms of trigger predicates, and so they also connect the triggers and the arguments. And the first 8 formulas in this MLN are hard constraints, meaning that they have infinite weights. Whereas the last formula encodes how a word W with trigger type T is related to the row A of its argument via dependency type D. And this is a soft constraint whose weight need to be learned. So the question is, how can we actually learn these weights? Well, we could use gradient descent to maximize the conditional likelihood using this familiar formula, weight update rule, where Nj is the number of groundings in which the J formula is satisfied in the training data, whereas this number is the expected number of groundings in which the J formula is satisfied given the current weight vector. And so computing this expectation requires performing inference over the MLN and is intractable. And so we instead use the voted perceptron algorithm, which, if you remember, approximates the number of satisfied groundings only in the map assignment. Okay? And in general, it's much easier to compute the map assignment than the expectation. And so we've talked about the second step, so let's take a look at how we encode the SVM output as prior knowledge in our MLN in the third step. We add 2 soft clauses into the MLN, namely the trigger type and the argument row clauses. Again, if you remember, the SVM trigger used in the baseline provides the confidence regarding how likely the word at position J in sentence I has triggered the type T. Whereas, in this case, the SVM argument classifier in the baseline provides the confidence regarding how likely the word at position K in sentence I has argument row A with respect to the token at position J. And so we can use these confident values from the SVM as the weights of these soft formulas in the MLNs. And so you can see that they provide prior knowledge for the MLN. And in this case, the high-dimensional features are implicitly used by the MLN. And in practice, we need to scale these confidence values. Okay? And so what's next? Well, we need to perform map inference, not only in testing, but also in training, meaning weight learning. So the question is how? Well, let me tell you, what the idea is. We want to decompose the network into several disconnected components, because otherwise, if we use the entire MLN, it's not going to fit into memory. So how can we decompose the network? Well, we make the following observation. All our predicates, if you remember, are sentence dependent. And what that means is that the map assignments to the MLN over all the sentences is the same as the union of the map assignments to the MLN over each sentence. And so what that means is that the map computation is decomposable. We can perform map inference for each sentence independently of the others. And so we can create one MLN per sentence and keep only one sentence grounding in memory. And that's how we manage to fit the MLNs into our memory. So let's move on to evaluation, where our goal is to evaluate our approach to event extraction. We use all 3 data sets from all 3 years of GENIA event extraction. The scores are obtained by submitting our output to the official online evaluation tool under the approximate span recursive evaluation setting. Here are the results on the BioNLP 13 test data. Here we show the results of the 5 best systems on this data set. Some are pipeline learning systems. One is the rule-based system, and there's also a joint model using subgraph isomorphism. And you can see that our system beats the best performing system. And here is a comparison with our combined MLN SVM approach with the baseline, which uses only SVM output in the pipeline manner. And you can see we have results over different types of events. You can see that the MLN SVM combined approach beats our SVM baseline by nearly 5 points, and so joint inference using MLN is indeed important. And in particular, the performance on the regulation events, which is, again, one of the hardest events to extract in this task, improves by 9.33%. And here are the results on the BioNLP 11 data set. Again, we show the results of the best system, BWA 12, RIDO 11, and then there are 2 pipeline systems. And the MIWA system in particular uses coreference features, and our system doesn't. So even without using coreference features, our system performs marginally better than MIWA 1.2's system and beats the best joint model and 2 other best pipeline models. And finally, we have results on the BioNLP 09 test set. And we again show the best systems on these data sets. We have seen MIWA 12 and RIDO 11 in the previous slide. And there are also 2 systems, pipeline systems without using coreference features. And there are also 2 MLN-based systems, Poon MLN and RIDO MLN. And here you can see that our system outperforms previous MLN systems, the best joint model, and pipeline systems without coreference features, but is marginally worse than MIWA 12, which again uses coreference features. So in summary, we presented a general approach for exploiting high dimensional features in MLNs, and we have obtained fairly good results on the 3 GENIA event extraction data sets. Thank you very much.
We have time for 2 questions.
Hi, Vincent. A very interesting talk. So I think if I understand correctly, what you're doing is basically using SVM as a way to do this kind of feature reduction before you send it to MLN. And it seems like you're not doing parameter learning in MLN because you're using the confidence for like the soft constraint as the weight for the clause. And for the other clause, did you do like any parameter learning?
Okay. So if you're talking about this clause, so in our MLN, we have 9 different formulas. So we have 2 kinds of soft constraints. One kind of soft constraints came from this particular formula where we try to model the interaction between a word, a trigger type, and the argument row that it is connected to via some sort of dependency relation. And so this is kind of a soft constraint. Whereas we also make use of these informations provided by the SVM. So these are we use the confidence from the SVM for these 2 soft clauses. So for these 2 soft clauses, we do not learn the weights. Whereas if you're talking about this last formula here, we do try to learn the weights from the training data.
Cool. So for evaluation, do you have any idea about your inference time? Like how long does it take for you to do the inference?
I guess the students would be able to answer this question. I don't know.
Yeah. All right, cool, thanks.
Hi, it's a very cool talk. So I'm just wondering, because we did something similar and we use like integer linear programming, I think that's another way for you to formulate these like constraints. So is there any difference or actually they're the same thing? Another thing is that, so you said you use SVM, the features as prior, but still like you could have very high dimensional features, right? So if you're still using all of them, like you still have multiple groundings, or are you actually doing some reduction from there?
Okay. So if we actually use all those word n-grams or high dimensional features directly in the MLN, of course, it's not going to return any output to you because MLNs cannot handle these high dimensional features. And so what we are essentially doing here is to use SVM to reduce all these high dimensional features into just one number, which we encode as the priors for these soft formulas. As far as the other question is concerned, is there any difference between integer linear programming and MLNs? The main difference is that integer linear programming, as far as I understand, is good at handling hard constraints. I'm not sure whether it's possible to handle soft or encode soft constraints. Whereas in this case, the weight learning, and also in MLNs, I'm sorry, in IOP, you're doing inference. You're not doing anything in learning. In other words, you cannot mess with the learning process when you're applying IOP. You can only take the output of whatever learning algorithm you use and then try to reconcile any contradictions that you see in the output to enforce your hard constraints. Whereas in MLNs, you actually mess with the learning process. You learn the ways of these soft formulas, and so you are making changes not only in the output but also in the learning process. So I believe those are the 2 major differences between Markov logic networks and interlinear programming.
Thank you very much. And just one final quick question. Like, so the argument and the event, can they be like across different sentences or always in the same sentence?
In the data set, there are, in fact, cross links, cross sentence links. But in this case, most of the, the links are within sentences. So we only handle within link events in this case. But if we want to further improve, we will have to handle, events that involve, multiple sentences. But of course, that would come at the expense of, again, more memory, and so we'll have maybe to have some other tricks to help us, reduce the memory requirement.
Hi, I have a question about you contrasted your approach to the one that was best in the past because it uses coreference resolution, but I think the results in 2013 suggest that coreference resolution probably does not bring that much. So is this really the only reason why your system could not beat the best system? I would doubt that coreference resolution really is the thing that does the trick.
Okay, I see. I'm not sure if I have further comment, but thanks for this observation.
Thank you.
Thank you very much.